Okay, so today we're going to look at Eulerian trails and circuits. So remember, this one begins with the E. So you know that this one, when the one that begins with the E is the one that has restrictions with the edges, okay? So a trail and a circuit that follows every edge in a graph. So if you have a network, so you've got your graph drawing, and remember a trail is a walk. Remember, a trail is a walk where you don't repeat an edge. Well, a Eulerian trail is a trail that uses every edge in the graph, okay? So every edge in the graph, without duplicating it, is a trail. And if you have a Eulerian circuit, it's just you use every edge once and you start and finish at the same vertex. That's if you have a Eulerian circuit. Okay, so so then we can find there's a few little facts that can help us decide whether this network has a Eulerian trail or a Eulerian circuit. So if a Eulerian trail will exist if the graph is connected. So that means that all the vertices are connected with an edge. So there's no isolated vertex. So if it's all connected and has exactly 0, so either you have 0 or 2 vertices that are odd degree. So remember, if a vertex is an odd degree, that means it has a degree of 1, 3, 5, etc. Okay, so if you have something like that, a Eulerian trail can be done. So if they're all even, you can get a Eulerian trail. If they're all even except for 2 of them, then you can get a Eulerian trail. With the circuit, they all have to be even. So a Eulerian circuit must have all even degree vertices. Okay, so that's the only way. So if you find an odd vertex in your network, you would not be able to get a Eulerian circuit. All right, so let's have a look at here. So it says in this question, for each of the following graphs, it says first determine whether it has a Eulerian trail or Eulerian circuit, both or neither, and state why. And the second, if it does have one, show the example. So let's have a look at, we'll do part I first. So what you want to do is you want to check the degrees of these vertices. So what's the degree of A here? Would be 2, yeah? B will be 2, C will be 2, and D will be 2. So can it have a Eulerian trail? Yes, because it's all even. And can it have a circuit? Yes. So this one you would say yes, it can have a trail and a circuit. And when we state why, and we just say because all vertices are even. Okay, and then part 2, it says to write one out. So it doesn't matter. Everyone will have could have a different circuit or trail. It doesn't matter, but as long as when you check it out. So what I might do is I've got to use every edge once. So I might go from, change that to the thing. I might go from A to C, C up to B, B to D, and back to A. So I have not gone over an edge twice, so I'll just write that out. I went A to C to B to D and back to A. Okay, so there's an example of that. One's an example of a circuit or a trail. Okay, so then if we look at the next one, so first of all we're going to see if we can get a circuit or a trail. So the degree of A is 2, the degree of B is 2, C is 2. Now the degree of D is 3, and the degree of E is 3. So because I have 2 odd, I can only get a Eulerian trail, and that's it. So I'm going to say a trail can be found. And we'll say because there is 2 odd degree vertices and the rest are even. Okay, and when you go to do a trail with and you've got the odd degree ones, what you need to do is you need to start and finish at the odd one. That's the way it can happen. So I've got to pick one of the odd ones. So I'll start with E, and I might go, all right, I'm going to go E to A to D to C to B to E and D. There's a trail, okay? So you can see I started at an odd and I ended at the odd. So I'll draw the arrows in there so you can see we went there, we went there, we went this way, that way, through here and there. So you can see I started and ended at the odd. So I'll just write that out, E to A to D to C to B to E to D. So you can see I did repeat a vertex but not an edge, and I started and finished at the odd one. All right, and now let's look at this last one. So let's look at the degrees of the vertices. So we've got 2, 3, this one's 3, this one's 3, and this one's 3. So neither a trail or circuit because there is more than 2 odd degree vertices. Okay. So it says determine whether the graph has a Eulerian trail or a Eulerian circuit, both or neither, and state why the graph has a Eulerian trail and show one example. So let's have a quick look. We're still doing the same thing. So we've got 2, 3, 3, 3, and 1. So what's this one? Can it have any? What do we think, boys? Can it have a Eulerian trail? No. No? Why not?
Because there's more than 2 odd vertices.
Excellent. So neither. It can have a neither trail or circuit because more than two odd vertices, and that's for a trail, and the circuit we would need all even. So let's have a look at the next one. I'll just do it in a different color so you're not getting confused. So this one's 2, the degree of D is 4, the degree of A is 2, and the degree of B is 4. So what can we have for this one? We can have a trail or, we can have a trail or circuit because all even vertices. And then it asked us to give an example of one. So you can start anywhere. So you can just go, all right, I'm going to start at C. I might go to D, then I'll go back to B, A, D, and C. You might have different ones, so it doesn't matter. As long as when I follow your pattern, you get, it doesn't go over an edge twice, okay? Okay, so that's my example, how I went. All right, and then let's look at this last one. So I'm going to check the vertices degree. So E is 2, A is 1, B is 2, C is 3, and D is 4. So what can I get with this one? A trail, and so a trail can happen, a Eulerian trail, and what can and why?
There's two odd.
Yeah, because two odd and rest even degree vertices. Okay, so then if I'm going to do an example of that, I'm going to start at an odd one. So I'm going to start at A, and because that's going to be the easiest. So I'm going to start at A, and off I go. So I'm going to go A to D. For me, I went up to E, back to D, to C, to B, to C. All right, so there, that one worked for me. So I went A to D, to E, back to D, to C, to B, to C. So you can see I started at the odd one and I finished at the odd one. So with this page is pretty important because what you'll see, it's for when you're in an exam or a test. So we won't tell you that you're doing a Eulerian trail, or we might not suggest. What they'll say is they'll use a practical application. So they might say here, the postie wants to deliver the mail and he doesn't want to travel along the street more than once. Well, that makes sense because he goes along the street. He's already delivered the mail there. So he wants to use all the streets, travel along the streets without repeating. So that's an example of a Eulerian situation. And if he starts at the post office and maybe ends at the post office, maybe it's a Eulerian circuit, could be possible. So that's what you have to think. They'll give you practical questions and then they might say, what is this situation? What type of, is this situation? What's the mathematical name for this? And you'll say it's a Eulerian trail or whatever. So another example could be a visitor to a tourist park wants to minimise the distance they walk to see all the attractions by not having to retrace their steps at any stage. So, so they don't want to double over an edge. So really that's a Eulerian trail or a circuit where they want to see every path, but they don't want to repeat it. Okay, or a road inspector, there you go, wants to inspect roads. So just handy to have because you might forget, you might be in doing your application task or your exam and you go, what type of situation is this? And this might help you refresh yourself.